All right, last time we found the normalized wave functions for the particle in a box problem, right? The expression that we're looking at right now is what we came up with for that. Here, again, n is a quantum number, and so n takes on values from 1 and upward in whole number increments. L in there is the length of the box, right? That's the size of the box, which is a parameter that we set. It's not a variable. And X is the actual position coordinate where within that range from 0 to L we are looking. Okay, so that gives us the wave functions for the solutions to the problem. The next thing we're going to do is to use the Schrodinger equation to find the energies for those wave functions. We're going to do that by finding the eigenvalues of the Hamiltonian that correspond to those wave functions. Before we do that, though, let's take a quick look at what the wave functions would look like. Okay, so I put in some plots here. On the left, we have the wave functions for n equals 1 through 3, and then on the right, we have what psi squared would look like. In both sets of graphs, we're going from 0 to L across the width of the box, right? And in each case, they're just sort of offset from one another so that we can see them all clearly. If we look at the wave functions themselves, they're sine functions, right? And so the n equals 1 solution has half a wavelength of a sine function going across the width of the box. N equals 2 has a full wavelength, n equals 3 has 1.5 wavelengths. So in each case, what we have is we have n half wavelengths, right? And again, that was because we have this boundary condition that said the wave function had to go to 0 at both edges of the box, right? And so the sine function will do that as long as the box corresponds to a whole number multiple of half wavelengths. If I come to the right-hand side, I have psi squared. Those are the probabilities. And notice that in all of these cases, I have a probability that has some maxima and minima in it, right? And so we've got regions of higher probability and regions of lower probability down to, in fact, if I look here at the midpoint in n equals 2, or at the 1/3 and 2/3 points in n equals 3, I've actually got what we call nodes, which are points along the x-axis where the square of the wave function goes to 0. That means the probability of finding the electron at those positions goes to 0, right? And so that's kind of a curious result that happens often in quantum mechanics. If we look at those, one thing we can see is that all of the wave functions, the ones we've got drawn there, the square of the wave function, the probability density function, is always symmetric about the middle of the box, right? That tells us, for example, the probability of being on the one half of the box or in the other half of the box. Those two probabilities are always the same. That means they're always, there's a 50-50 chance that the particle is on the left-hand side or the right-hand side, because there's nothing that really distinguishes one side from the other. So we probably would expect them to be an even chance, okay? All right, let's leave that and go back to work on getting the energies. So here is our Schrodinger equation, right? The Hamiltonian is only the kinetic energy part. We already have the wave functions. If I take the Schrodinger equation itself and rearrange it, I can get this form here, which says I want the second derivative of the wave function can be set equal to the quantity on the right-hand side up there, right? All that really involves is multiplying the constants, so taking this piece and moving it from the left side to the right side to do that, okay? So in order to do this, we want to find that second derivative. So let's start by taking the derivative. And if I do that, what am I going to get? I'm going to get an n pi over L from inside. I'm going to get a square root of 2 over L from the normalization factor, and I'm going to get a cosine of n pi x over L. Okay, so that's the first derivative. I need to do the derivative one more time, so I'll just do then psi squared, or second derivative rather, of psi. And that one is going to be equal to what? I'm going to get another, I'm going to get a minus sign because I do the derivative of cosine, so I'm going to get minus, I'm going to get my n pi over L back again, so I'm going to call this n pi over L squared. I'm going to get I'm going to still have my normalization factor. My square root of 2 over L is still along for the ride. And now my cosine function is going back to sine. N pi x over L, right? And if I clean that up a little bit, I can call that, let's see, I can call that minus n pi, sorry, over L squared. And this piece here is just my original wave function, right? So I'm going to write that like this. Okay, so that will tell me that that's what I get down there. This is the second derivative. Up here it says the second derivative is equal to that. Okay, so that means I can take the pieces in front of the psi in both of those expressions and I can set them equal to each other. That'll give me minus 2me over h bar squared equals minus n pi over L whole quantity squared, right? If we take that and solve it for E, I'm going to write it as E, and I'm going to put a subscript n on it because there's a different energy associated with each different value of n. And what I get is that the energy for state n is equal to n squared h squared over 8ml squared. And if you look carefully at those, you'll see, for example, that over here I had a pi, and I've lost the pi. The way I've lost the pi is because I've changed from having h bar in this piece, and I've replaced that now with ordinary h here. Right? Remember, h bar is h over 2 pi, and so that's how I did the cleaning up of that to get a version that just has Planck's constant itself in it rather than h bar. So this expression here gives us the energy for state n. Right? It says the energy depends on n squared, where n is the quantum number, right? So the higher up in quantum number I go, the higher the energy of my state will be based on that equation, all right? Let's take a look at exactly how those things space out in an energy level diagram. So these are the equations for the wave function and the energy over here. In this version of the diagram, what it's got is it's got the wave functions on the left and the wave function squared on the right again. Only drawing the first three, we could keep going up to higher and higher energy levels here. In this diagram, the baseline for the wave function and for the psi squared, these levels here have been offset to reflect the actual energies of those states, right? So the first thing to notice is that the energy of the n equals 1 state, n equals 1 is the lowest state, but even that state has a non-zero energy, right? This is what is referred to, as it says over here, as 0-point energy. We could say that this has a non-zero 0-point energy, but often we just say it has a 0-point energy. That says that the energy for the particle, as long as it's trapped in the box, can never go to 0, right? That's because if I look at this, the smallest value of n is 1. If I put 1 in for n there, I definitely don't get 0, right? Because I've got finite values for all the terms on the right-hand side. So I'm definitely going to get a non-zero energy when I do that. As I climb the ladder in quantum number, I go up in energy. And in fact, as I go up the ladder, the steps on the ladder are getting farther apart, as reflected in our diagram here, right? The only thing that changes when I go from one state to another is n squared, right? So n squared for n equals 1 is equal to 1. N squared when n equals 2 is equal to 4, right? And then n squared when n equals 3 is equal to 9. And so the spacing here, if I look at, say, this distance, that's the energy difference between n equals 2 and 3. That's definitely larger than the energy difference that I can mark over here between n equals 1 and 2. Right? And so that's showing us that as we go up in energy, these states are getting farther and farther apart. Because the walls in the box are in fact infinitely tall, meaning the potential goes to infinity on the other side of the wall, that says this ladder could keep going infinitely high in principle. Right? There would be a limitless number of actual bound states. But the other thing that's interesting is that no other energies are possible, right? So this is very much a quantized situation. As long as the particle is trapped in the box, it can have an energy that's given by this expression for any whole numbered value of n, but it can't have any other energies, right? So I can never have this particle have an energy that corresponds to this level here, for example, right? It's just fundamentally not possible for the particle to take on that energy. That's a quantization effect. It's something that's very much at odds with, again, sort of your intuitive experience from macroscopic objects, because in macroscopic objects, we'll eventually see, to the extent that energies might be quantized, the separation between those levels is so small that it's of no consequence, and that we would never be able to be aware of it in any case, because the steps would be very, very small. Right. So yeah, we point out that we get a discrete set of wave functions here, right? For the free particle, because there was no boundary condition, really. It just had the same potential energy no matter where it went. And that meant that there would be a kind of limitless number of solutions in that case, right? The fact that we do have boundary conditions here, expressed in the fact that we required the wave function to go to 0 on both ends of the box, and that came from the fact that the wave function has to be continuous. That's what gets us quantization, right? The fact that we get a quantum number, one of the things that's nice about this problem is it's simple enough to tell that the quantum number kind of just happens, right? That you're doing the math and you're saying, well, those points have to stay fixed. The only way for that to be true is for there to be a half integer number of wavelengths of that sine function going across the box, right? So it isn't that we set out to say, I really want this problem to be quantized. It's just we work through the problem and we get the result that there is that index in there, the quantum number, right? In this case, we did a one-dimensional problem and we got one quantum number. We'll go on to see that if we make the problem relax the restriction to be one-dimensional, go to 2 dimensions or 3 dimensions, each time I do that, I'll pick up an additional quantum number, right? The allowed values of n are restricted, and again, the restriction, the fact that they have to be whole numbers, that falls out naturally from the math, right? If you remember when you were taking general chemistry, someone, maybe me, I don't know, someone probably made you remember all sorts of rules about quantum numbers, right? That said that the n quantum number can be 1, 2, 3, and so on, that the L quantum number goes from 0 up to n minus 1, and so on. All those different rules come out of the mathematics, right? They're not things that were just sort of arbitrarily made up to make things hard for students to remember. They're really what happens if we just do the work of solving the problem. Let's take a look at some other properties. Let's look next at the momentum for the particle in a box. Okay, so my wave function is a sine function. If we think back, remember the momentum operator looks like this, and so the momentum operator is only got a single derivative in it, right? I start with a sine function, I take the derivative, I'm going to get a cosine function, I'm not going to get a sine function again, right? So my wave functions are definitely not eigenfunctions of that momentum operator. That means that my states in the particle in a box do not have a fixed momentum to them, right? If I want to find the momentum, or get an idea about the momentum, I could go back to this classical relationship here, right, which says that the kinetic energy is related to the momentum by that expression there, right? We know the energies now. The energy expression is just the one we just derived, n squared, h squared, all that stuff, right? So we could, and the energy is all kinetic, right, because the potential energy is 0 as long as we're inside the box. And so I could equate this energy expression with this kinetic energy expression. When I do that and solve for P, what I get is this expression where everything is squared, which means that if I take the square root of that, as it says there, I get 2 possible momenta, right? I get plus or minus and a value, right? This is the same argument as we made about the free particle, right? My particle is in the box, it's moving back and forth between the walls, but there's an equal probability that it's going this way versus going that way, right? And if it's got a particular kinetic energy, it's traveling with a particular speed. If it's going in opposite directions, then it's going to have opposite momenta when it does that, right? So if we actually put the momentum operator into the expectation value setup with the wave function here, what we would find is that the expectation value of momentum should be 0. That's because there's a 50-50 chance that it's plus this amount and a 50-50 chance that it's minus that amount when I take those things and weight them equally, the average is going to be 0. Okay, even though if I could measure the momentum, no individual measurement would give me 0. The average of lots of measurements would still be 0, right? And that's what our expectation value is supposed to tell us, and does tell us in this case. Right, we're going to do, a couple calculations here related to an electron in a 1 nanometer box. That would correspond to something that was about 5 atoms long, right? If I had a 5-atom chain and my electron was somehow free to slide along that, that segment of molecule, that would be about a nanometer typically, okay? First thing we're going to do is find the minimum energy, what would generally be called the ground state energy, or we could call it the 0-point energy. That's going to be the energy that corresponds, because it says minimum, right? That's my clue that tells me I want to do this with n equals 1. And so that's relatively straightforward. I just have to plug some terms into the energy expression. Then we're going to find a couple of probabilities. The first one is a probability for finding the particle in a very small slice at the center of the box, right? The center of the box, the probability density function is at its maximum for that n equals 1 state, right? And so I'm going to expect to find a decent probability of that. Then I'm going to find the probability for finding the electron over near the wall, but the region I'm looking in now is much wider, right? This is a 10 times as wide portion of the box up against the wall, and so we'll see how those two probabilities compare when we do this, all right? All right, the first part is the easiest. So let's just find this energy for the n equals 1 state. So I know my expression says En is equal to n squared h squared over 8 ml squared. All right, I want to do this for n equals 1, and so I could write that E1 is equal to n squared is 1, so I'll just write that in there explicitly, even though it's not going to do anything. I get 6.626 Planck's constant. Again, working in SI units, as is my general preference. I've got 8. I need the mass of an electron, which is 9.1 times 10 to the minus 31 in kilograms. And then I need the length of my box. My 1 nanometer is going to be 10 to the minus 9 meters. So I'm going to put that in there that way. And that's squared. Okay, and h is squared up on top, okay? If we don't remember to square h, we'll get a very different answer. And if I take that and multiply them all out, my notes tell me that I get about 6 times 10 to the minus 20 joules. Okay, that's a reasonably small energy, right? We've seen that energies for visible light photons are about 10 to the minus 19 joules typically, but it's a reasonable, a credible order of magnitude for the energy of an electron. Right? If I had, for example, forgotten to square h up there, then my answer would have shifted by 10 to the 34th power, and then hopefully when I got an answer, I would have realized that it was a ridiculous answer, because I would have had an electron with an enormously large kinetic energy if I left off a 10 to the minus 34 term on the top, okay? So that tells me that this should be my energy. The energy will work out to be in joules. If you want to confirm that, you just have to reconcile what you've got kilogram meter squared on the bottom, and you've got seconds squared on the top. So that's effectively 1 over joules, and then you've got joules squared on the top. And so you should land on joules if you parse all those units out successfully to make sure things are in the right place. All right, next up, we're going to find the probability for finding the electron in a region right in the center of the box. So remember what our probability function looks like. If this is my box, right? My probability function looks a little, that's a little lopsided, but pretend that's in the middle, okay? I've got a narrow slice right at the center, so I'm looking at a region in there, okay? Because my slice is very narrow, and because it is being cut at the part right at the top where the chi squared function is not changing very sharply, right? What I'm going to do for this one is I'm going to make a simplifying assumption, and I'm going to assume that I can just call psi squared constant across that range. So I'm going to find psi squared at 0.5, and I'm just going to essentially do that, the integral under the curve in that region as if it's a rectangle rather than something with a slightly curving top. Okay, if you want, you could do the problem the other way and check how much of an error I introduced by this, but it's pretty small. I don't actually have the number handy, so I'm not going to declare how small I think it is, but it is a pretty small amount. Okay, so let's go ahead and see what I have to do to get that. Okay, my probability should be given by the integral. In principle, it's the integral from the first, well, I'm not going to do the integral here, so let me not write it that way, but it would be the integral of psi squared dx, okay? What I said I'm going to do is I'm going to make this a rectangle, so I'm going to find the value of psi squared at 0.5, because that's the midpoint of my, my region here, okay? And so psi, let's do psi first. Let's do psi 1 of 0.5 nanometers. So this is the value of the wave function at halfway across the box, right? Remember, psi is always equal to square root of 2 over L sine of n pi x over L, where x is equal to 1. So I wrote an n in there when I should have really written a 1, but that's okay. And so if I put in the quantities for this, this is square root of 2 over L. I'm putting L in here as 10 to the minus 9 meters, because that's the length of my box. Then I've got sine of 0.5 pi over 1. I'm sort of being a little bit weird with units. Over here, I've put things in meters because I want to end up that way. In here, I've put both the 0.5 and the 1 in nanometers. The important part is that I have nanometers on the top and the bottom. So the argument of my sine function is still gonna be unitless. And in fact, that's sine of 1/2 pi, right? So this thing is very much just equal to the piece in front, to square root of 2 over 10 to the minus 9 meters. Okay, if I take psi squared at halfway across, that says I'm just going to get rid of the square root, so I will have 2 over 10 to the minus 9 meters, which will be equal to 2 times 10 to the 9th, with units of 1 over meters. The 1 over meter unit is a little bit strange looking there. The reason for that is this is the probability density function, and it's a density in 1 dimension, right? So you think of densities as being something per unit volume. Because it's 1-dimensional, the equivalent of density is going to be per unit length. And so that is the value of my function up here. So what I've said is that the height there is this quantity, right? So all I want to do is I want to get my probability to be equal to psi squared times, let's say, delta x, where that's the width of my region, right? So that's going to be my 2 times 10 to the 9th meters to the minus 1. And now I'm going to multiply that by 0.02 nanometers, right? And so I should have written that, let me make that 0.02 times 10 to the minus 9. So it's in meters to go with inverse meters over there. If I take those and multiply them out, the 10 to the 9th and the 10 to the minus 9th are going to take care of one another. And I'm going to be left with that being equal to 0.04, right? Which says that I have about a 4% chance of being in that very small slice at the center of the box, right? I said that this was the region of the highest probability. 4% might seem small, but then we have to realize that it's only 1/50th of the box altogether, right? So in 1/50th of the box, I've got what is, I guess, 1/25th of the probability, and that is a reasonably large value, therefore. When I come to this one, let's resketch the probability function here, probability density. Now I'm looking at a probability for a slice over here, okay? In this one, because I'm now off on the wings of the function, the slope is rather severe, right? So it's pretty obvious looking at that calling that area a rectangle would be a really bad idea, right? So I'm going to actually do the integral this time, because what I want to do is I want to take the integral under the area under that curve in that region. That should be the probability, right? So for this one, I'm going to have to set up and say my probability is equal to the integral from 0 to 0.2 nanometers, okay, of psi squared dx, which is equal to, when I square psi, I start off with that square root of 2 over L, but I get it twice. So I've got this piece in front. All right, that's just my normalization factor. Then I've got the integral from 0 to 0.2 of sine squared. N is still 1, so we'll just say pi x over 1 nanometer. Just like before, my units here, because x is in nanometers or implicitly in nanometers because I have the limits that way, and I have my dx here, right? That's going to give me my piece in front, which is 2 times 10 to the 9th meters, 2 times 10 to the 9th inverse meters, right? And that's going to be multiplied by that integral. That integral happens to be 1/2 x minus 1 nanometer over 4 pi. And again, I just look up the form of the integral for this. I'm sine of 2 pi x over 1 nanometer. And that thing has to be evaluated at the limits, 0 and 0.2 nanometers. When I do that, I'm going to get the 2 times 10 to the 9th out here. And my integral piece is going to go to 0.1 nanometer minus 1 nanometer over 4 pi sine of 0.4 pi, which my notes here claim is equal to 0.0486. All right, so that says that I've got a 4 or 5% chance of finding the particle in this region. Now, at first it feels weird that I had a 4% chance last time, and now I'm saying I've got an almost 5% chance now when I've moved over to the part where the probability is supposed to be much smaller. The thing to keep in mind, though, is now I've got a region which the width of my region now is from 0 to 0.2. So my window is 10 times as wide as the narrow slice that I put in the center. Right, so the fact is that the probability density is much higher at this midpoint, but I'm just integrating over a much wider space as I do this, right? That illustrates pretty nicely the way we can go about finding things like these probabilities, right? Sometimes you can see them fairly clearly, right? Like if I looked at, when I said before that the probability of being on the left side or the right side has to both be 50%, right? If I look at that for any of the wave functions, that's got to be true. If I looked at the n equals 3 wave function where I've got 3 maxima, I could easily say that the probabilities for the 3/3 of the box, the first third, the middle third, the third third, all have to be equal in that case, right? In other instances like this one, there's no obvious way to just say I can look at that and figure out what it's going to be. It does help to be able to say, yeah, that seems like it's not wildly unreasonable, or it does seem like it's wildly unreasonable, but you do in some cases just need to do the math. All right, we're going to do at least one more segment about the particle in a box as we, in that one, we'll focus on the spacing between the energy levels and start to talk about the idea of having transitions from one energy state to another, which will point us in the direction of spectroscopy. Thanks.